to solve them, as I have told you that, by the way, all this term, I have not really complicated things. This is in the absence of any torque. That's why you could use L dot equals to 0. If there are torque, this right hand side which are 0, like which are homogeneous equation, because there are no source term, then there will be torque, tau 1, tau 2, tau 3, if there is a torque. But I hope they won't give you, because I think no one has done it, means in the other batches. If you try to talk to them, they have done it without any external. And that's why we could use it, right? Yeah, easy. Other than that, this simple, mostly looking set of equation will become again difficult. And, okay, now we can solve them. So one of the example I have already told you, just to write the first example, which is very trivial case. I1 equals to I2 equals to I3. This is sometimes called complete rotational symmetry. Complete rotational symmetry. Okay, so in this case, for example, all the omega I will be constant. For all I1. As we have already said, because the second term will vanish because I1 equals to I2 equals to I3. So all of this term, this will be 0. So you will get I omega 1 dot equals to 0, I omega 2 dot equals to 0, I omega 3 dot equals to 0. Why all of them are? Because they are equal. So omega, all the component, omega 1, omega 2, omega 3, they will be constant. Now the second interesting case, I1 equal to I2, which is not equal to I3. You might say, I know that. You did it. Ix equals to Iy, not equals to Iz. Oh, that's nice. Okay, so let us just see what because you can solve all those equations from Lagrange that we did, find your moment of inertia. Also, you can solve Euler equation. These probably you have not done in undergrad, or it was done in undergrad. So this is a new thing. So, for example, an object like this could be, this is the I3 axis, because we have to do it in the next class, so let me tell you, इसको लट्टू बोलता है, okay? So I don't know how you call it in
Yes, sir.
So yeah, it's a top, okay? So it's a symmetric top, and that's why you can see there is an axis of symmetry. This is actually symmetric solution because along these two axes they are symmetric. So Ix and Iy usually they are symmetric. I1 equals to I2. So the moment of inertia in the transverse plane they are equal, and this is the longitudinal plane. Okay, so if you try to solve this equation, the first one will be I1 omega 1 dot equals to omega 2 omega 3 I1 minus I2. Right? Oh, it will be I2. Oh, but yeah, I have used this. Fine? The first equation will be I1 omega 1 dot. I have taken on the other side. I2 minus I3, but I2 is equal to I1. So, then the second equation will be I2 omega 2 dot, but I2 is equal to again I1. Then it will be omega 1 omega 3. I3 minus I1. Right? And the third equation, which will be I3 omega 3 dot, will be equals to 0. Because we will have a term which are equal. I1 equals to I2. So you see, in this case, the third equation is very simple, like this. So omega 3 is constant. So the half component or the component of this omega angular velocity vector along the symmetry axis, along the axially symmetric direction, that is constant. So you know this will rotate with a constant speed. And now you have a set of equations. Then you can easily solve them again. Again you can solve them. Can you see this is a very known equation? I will just let you observe that they are very easy equation. I will define something. I will define a quantity omega, which is equal to omega 3 times I1 minus I3 by I1. Right? If we do that, I1 minus I3 by I1, then